Today let's talk about natural numbers and mathematical induction. Inductive subsets of R. Definition: A as a subset of R is said to be inductive if 1 belongs to A, and if X belongs to A, then X plus 1 belongs to A. Examples of inductive sets. R plus is inductive. Proof: 1 belongs to R plus, and if X belongs to R plus, then X plus 1 belongs to R plus by the order properties of R. T equals to the set containing all real number x such that x is greater than or equal to 1 is inductive. Proof: 1 belongs to T. Also, if y belongs to T, then y plus 1 is greater than or equal to 2, which is greater than 1. Then y plus 1 belongs to T. Natural numbers. We denote the set of natural numbers by n. Definition: let C be the collection of all inductive subsets of R. Then n is equal to the intersection of the elements of C, which is equal to the set containing all x such that x belongs to S for all s belonging to C. In other words, n is the intersection of all inductive subsets of R. Theorem 1. If A is an inductive set, then n is a subset of A. Proof: let C be the collection of all inductive subsets of R. Let n be a natural number, then n belongs to the set containing all x such that x belongs to S for all s belonging to C. So m belongs to S for all s belonging to C. As A is inductive, A belongs to C, then m belongs to A. Therefore, n is a subset of A. Claim 1. If n is a natural number, then n is greater than 0 and n is greater than or equal to 1. Proof: as R plus and T which is equal to the set containing all real numbers x such that x is greater than or equal to 1 are inductive, we have n is a subset of R plus and n is a subset of T by theorem 1. That means all natural numbers are positive and they are greater than or equal to 1. Theorem 2. N is inductive. Proof: let C be the collection of all inductive subsets of R. Then n is equal to the set of all x such that x belongs to S for all s belonging to C. 1 belongs to all inductive subsets of R, so 1 belongs to n. If y belongs to n, then y belongs to all inductive subsets of R. Then y plus 1 belongs to all inductive subsets of R. Then y plus 1 is a natural number. Principle of mathematical induction. Set theoretic formulation. If S is a subset of n and S is inductive, then S is equal to n. Proof: as S is inductive, we have n is a subset of S by theorem 1. Since S is a subset of n and n is a subset of S, we have S is equal to n. Principle of mathematical induction. Usual formulation. Let Pn be a predicate with variable n. Suppose P1 is true. Further, suppose that for any k in n, if Pk is true, then Pk plus 1 is true. Then Pn is true for any n belonging to n. A predicate is a statement that is either true or false, depending on the value of n. Proof: let S be the set of all n belonging to n such that Pn is true. By definition of S, we know that S is a subset of n. As P1 is true, 1 belongs to S. Let K be a natural number. Suppose K belongs to S, then Pk is true. Then Pk plus 1 is true by assumption. Then K plus 1 belongs to S. Therefore, S is inductive. We have S is equal to n by the principle of induction, set theoretic formulation. So Pn is true for any natural number n. Integers and rational numbers. We denote the set of integers and rational numbers by z and q respectively. Define z is equal to n union the set containing 0 union the set containing all negative n such that n is a natural number. Define q to be the set containing all p over q such that PQ are integers and Q is not 0. Theorem: R plus intersect Z equals N. Proof: R plus intersect Z is equal to this expression by definition of Z, which is equal to this expression by distributivity. Just examine these three sets in brackets, this set, and this set. Okay, as N is a subset of R plus by theorem 1, we have R plus intersect with N is equal to N. As X belongs to R plus implies X is non-zero, we have R plus intersect with the set containing 0 is actually an empty set. Let Y belongs to the set containing all negative n such that n is a natural number. Then Y equals negative n for some natural number n. As n is a subset of R plus, n belongs to R plus, then negative y belongs to R plus since negative y is equal to n. Then y does not belong to R plus. Therefore, R plus intersect the set containing negative n such that n is a natural number is actually an empty set. We have R plus intersect Z equal to n union empty set which is equal to n. We conclude that m is a natural number if and only if it is a positive integer. Claim 2. There is no natural number x with 0 less than x less than 1. Proof. Suppose there is a natural number x with 0 less than x less than 1, but x is greater than or equal to 1 since all natural numbers are at least 1 by claim 1. Contradiction arises, so the claim is proven. Claim 3. If n is a natural number and n is greater than 1, then n minus 1 is a natural number. Proof. Let S be the set containing all natural number n such that n is equal to 1 or n minus 1 is a natural number. Then S is a subset of n by the definition of S. 1 is equal to 1, so 1 belongs to S, since we meet the requirement here. Assume K belongs to S, then bracket K plus 1 minus 1 is equal to K, which belongs to S. As S is a subset of n, bracket K plus 1 minus 1 is a natural number. Then K plus 1 belongs to S, so S is inductive. By principle of induction, S equals to n. Let n be a natural number, then n is equal to 1 or n minus 1 is a natural number. Suppose n is greater than 1, then n minus 1 is a natural number. There is no natural number x with 1 less than x less than 2. Proof. Suppose there is a natural number x with 1 less than x less than 2, then 0 less than x minus 1 less than 1. Also, x minus 1 is a natural number by claim 3. This contradicts with claim 2, which states that there is no natural number between 0 and 1, so the claim is proven. Claim 5. For any natural number n, there is no natural number x with n less than x less than n plus 1. Proof. Let Pn be there is no natural number x with n less than x less than n plus 1. P1 is true by claim 4. Let K be a natural number. Assume Pk is true. In other words, there is no natural numbers x with K is less than x less than K plus 1. Suppose for a contradiction that there is a natural number y with K plus 1 less than y less than K plus 2. Then K less than y plus 1 less than K plus 1. As K is greater than 0 by claim 1, we have K is greater than K plus 1 which is greater than 1. Since y belongs to n and y is greater than 1, we have y minus 1 is a natural number by claim 3. This contradicts the induction hypothesis, so Pk plus 1 is true. The claim is true by the principle of induction. Finally, by claim 1, all natural numbers are at least 1. Claim 5 states that for any natural number n, there is no natural number x with n smaller than n plus 1. By repeating using this claim, we have no natural number between 1 and 2, no natural number between 2 and 3, no natural number between 3 and 4, and so on. Therefore, the set of natural numbers is equal to 1, 2, 3, 4, and so on, which is our usual understanding of natural numbers. This is the end of the video. If you find my video interesting, please consider subscribing to my channel, liking my videos, and commenting down below. Thank you. See you in the next video.